Welcome to Lecture 10. This is the first lecture in a new unit. This unit will focus on radioactive decay. In this first lecture, we are going to first focus on different decay modes. We will focus on 4 specific types of decay modes and calculate Q values for each of those. We use the Q value to determine how much energy is released, but also the sign of that Q value helps us know if that particular type of decay is going to be spontaneous or not. And then we'll look at some of the online resources, understand the role of energy level diagrams, and step you through a couple of different nuclide chart resources to make sure that you understand how to navigate that information and understand what you're looking at. So radioactive decay is defined as the spontaneous process that an unstable isotope emits energy and particles from the atomic nucleus. So this word here, our spontaneous, what that means is that our Q value is 0, or Q value is greater than 0. So if we calculate a Q value, if we want to identify that this process is spontaneous, then we better find a Q value that is positive. And that does not necessarily mean it's going to happen, and we don't know the rate at which that will happen. We'll talk about that later on in this unit. But the fact that Q value is positive means that it is possible to happen in a spontaneous fashion. We don't have to put energy in order for that to happen. That was the whole definition of the Q value back when we first looked at it earlier this course. And when we say unstable isotope, when we say unstable isotope, what we're talking about is a radionuclide. A radionuclide is an isotope that is by definition unstable. And so here's the general equation down here that we would have for any kind of decay. We've got this being our unstable isotope. And this is going to be called the parent isotope. And it decays into what we'll call the daughter product, and then one or more possible light products. And depending on the type of decay, that's what dictates what those light products are and what the daughter is in reference to the parent. So there are nearly 2,700 known radioisotopes. Only 65 of those actually occur naturally. Everything else is man-made. And so this chart down here is the nuclide chart, which we're familiar with at this point, hopefully. And this is color-coded in terms of the types of decay. And we'll go over each of these types here. Not each and every one of these types, but the ones that you see that are predominant. And so this pink region down here, this is our beta minus decay. This region up here is going to be our beta plus, or electron capture. The yellow region up here is what's known as the alpha decay. And if you can see these green, I guess apologies to those who are colorblind. But there's scattered dots in this high mass number region where we have what's known as spontaneous fission. And so there's a number of these radioisotopes that, unlike U-235, we don't need to even target this with a neutron. They are going to undergo some spontaneous fission. The ones in the middle here, these black ones, are my stable isotopes. And so you can see more or less those exist in the center of this nuclide chart. We've got some on the right, some on the left of that stable isotope region where we've got radioactive decay from either one source or another. These regions up here, this is going to be a proton decay. And it's a little hard to see these purple ones up here, but this is a neutron decay. And there's a handful of radioisotopes that actually experience proton or neutron decay. We aren't going to focus too heavily on those. We're going to spend most of the time on our beta plus and our beta minus, beta plus / electron capture, beta minus, our alpha decay, and then the fourth one that we're going to focus on is a gamma decay. So these three plus a gamma decay, and that's how we'll term them. Focus, we've got beta plus, or we'll just broadly call that beta, and that just includes the electron capture option too. But we've got beta, we've got alpha, and we've got gamma. So those are the three focus areas that we'll be dealing with here in terms of decay in this lecture. So let's go through each of these. First, we'll start with gamma decay. What's happening here is that the nucleus is in an excited state, and it's going to decay down to a ground state. And in the process of doing that, it's going to emit a photon. And so the reaction looks something like this. We've got some number of protons, some number of nucleons, and here's our parent product, and it is in an excited state and has some number of neutrons, and that's going to decay into the same number of protons, same number of neutrons and nucleons, but because we're going from excited state down to a ground state, it's going to emit this gamma radiation. The second one is our alpha decay, and in the alpha decay we have our parent radioisotope, and that's going to decay into a new isotope. And the alpha particle you see in this diagram, it consists of 2 neutrons and 2 electrons, and so our proton numbers are going to decrease by 2. Our neutron numbers are going to also decrease by 2, which means our mass number here is going to decrease by 4. And then plus an alpha particle, which is often going to just be labeled helium-4. Okay, and then we have 2 types of beta decay, beta minus and beta plus. And if you remember looking at just generally the trends that you see here, you've got the stable isotopes in the center, and to the right of those or below those stable isotopes is the beta minus decay, and above those stable isotopes is the beta plus decay. And so in a beta minus decay, what's going on is a neutron in the nucleus changes to a proton, and in the process of changing to a proton, it emits an electron and an antineutrino. So here's my antineutrino here, and so what this looks like from the reaction standpoint, I've got my parent, and that's going to decay into it's going to experience a beta decay. And what happens is, because I had a neutron change to a proton, I didn't change the total number of nucleons, and so I still have A here, but my protons increased by 1 and my neutrons decreased by 1. And so this here, these stay the same. And so from if you look at the chart of nuclides, then you're going diagonally up to the left in that decay process. And then also on the right hand side, we've got the antineutrino. We'll put that over here. And then we have this electron, and in order to distinguish it more properly from an electron that is a molecular electron, this electron, it's not that there was an electron in the nucleus, but the source of that radiation, that particle, came from the nucleus. As the neutron changed to a proton, it emitted this what has the same mass as an electron, same charge as an electron. But a lot of times you'll see instead of labeling it with a E minus, that a lot of times you'll see just beta minus. But keep in mind it's the same mass as an electron, and in this case it's the same charge as an electron. So that's our beta minus decay. Beta plus decay is related to this, but I've got a neutrino instead of an antineutrino. And the antineutrino and the neutrino are extremely small. They're not massless, but they are extremely small mass, so small that we are eventually going to, when we get into Q-value calculations, we're going to neglect the mass, the rest mass of those neutrinos. But any kind of beta decay, you are accompanied by either an antineutrino in the beta minus scenario or a neutrino in the beta plus scenario. And it was early on in the 20th century that it was thought that these existed, and the reason for that is because there was an energy distribution to this beta particle that was emitted as part of the beta minus or beta plus decay. And because there was a distribution, that meant there had to be some other particle that shared the kinetic energy that came on the product side of that reaction. We measure the kinetic energy of the daughter, we measure the kinetic energy of the beta particle of this electron, and those two were different for every experiment. There was a distribution to that. And the only way that makes sense from a momentum conservation standpoint is that there was this third particle in there somewhere. And the actual measurements of that came decades later, but anytime you have a beta decay, positive or negative, you've got either an antineutrino or a neutrino that's emitted there. So with our beta plus, then, this looks like the following. We've got our parent, and this decays into a daughter. In this case, we're going to lose a proton because instead of a neutron changing to a proton, we have the opposite. We have a proton changing to a neutron. And so I have one less proton and one more neutron. But again, the total number of nucleons stays the same, just like it did with the beta minus decay. And the remaining components on the product side are going to be my beta plus particle and then a neutrino. And the beta plus particle is going to have the same mass as an electron. It's just going to have a charge of +1 instead of -1. And closely related to this beta plus decay is the electron capture here, which instead of an electron or a positron in this case, that's what this beta particle would be. So this is often called positron decay, the beta plus decay. But instead of an electron or positron originating from the nucleus, we are talking about an electron that's already in the electron cloud, in the molecule, in the atom, getting absorbed in, and then ejecting out some X-ray. And so this is now my molecular electron, not the electron that is represented by the beta plus or beta minus particle. And what this looks like here is the same as it did for beta plus, except for here we just have the neutrino. We don't have the electron. We don't have the positron. We don't have that out there. And so it's important to recognize that these two are the same. My parent is the same and my daughter is the same for both beta plus and electron capture. And a lot of times when you look these up in like the chart of nuclides and see what kind of decay there is, a lot of times these are listed together, the beta plus / EC. So they compete, and at the end daughter product is the same in either case. And you can see in the chart of nuclides, if I'm beta plus or I'm beta minus, then I'm going towards the region of stability. That's my beta minus, and my beta plus is also going to start out here and go towards the region where I have stable isotopes. And so for all these radioactive decay processes, what the molecule, what the atom, what the nucleus is trying to do is trying to eventually get to a stable isotope. And we'll talk about decay chains at the end of this, where we have something that has a high mass number and has this type of decay, and then that one's still unstable, so it has another type of decay, and it keeps going and going until it reaches some isotope that is stable and is no longer radioactive. Okay, so let's summarize all this by looking at the following chart. So this would be in the center here, this would be my original nucleus. And if I have, and so this is organized in terms of Z and N, just like a nuclide chart would be. So if I have an alpha decay, for instance, then I lose 2 protons and I lose 2 neutrons. And so that's why you see the alpha out here and the alpha in. If I were to absorb an alpha, then I would go up 2 and over 2, over 2 and up 2. And the same thing if I had a helium-3, then I go over 1 and up 2, or a deuteron, or a proton, or a neutron. Here is my beta plus and beta minus, so wherever I'm at, if I'm going through a beta minus decay, I'm going up and to the left. If where I'm at, I'm going through a beta plus decay, then I'm going down and to the right. But if I had other types of decay where I lose a deuteron or a tritium nucleus, then I can, it's a simple nucleon balance to help me understand where I need to go from where I'm at in terms of the type of radioactive decay. So let's look at a couple of online resources for this decay. One that I find helpful is from the IAEA, this chart of nuclides here. And it's a little buggy, but the thing I like about this is if I type in a specific radioisotope that I'm interested in characterizing, so U-235, let's say, then if I hover over this, then I can see the type of decay. The type of decay is going to be alpha decay 100% of the time, as I'm going to have an alpha decay, and so I'm going to go down 2 and over 2. I can see the same information down here in this table down here. I've got alpha, and this is the branching ratio. So sometimes there's a very small chance, 7 times 10 to the minus 9 chance that I go through spontaneous fission, that this U-235 just spontaneously undergoes fission. Every other time, so about 100% of the time, then I'm going to go through an alpha decay. And we'll talk about this half-life in a coming lecture, but this represents the time, if I had a sample, that it takes for half of my molecules or half of my atoms to convert or go through that decay process. But the thing I like about this is, there's a couple things I like about it. It highlights all the other isotopes that are of interest in this chain, whether I'm going up or down the chain. For instance, if I go here to protactinium, then you'll see that it is a beta minus decay, and therefore it is a parent of U-235. U-235 is a parent, since I'm going through alpha decay, I got to go down 2 and over 2 of thorium-231. And thorium-231 goes through a beta minus decay, and so it's going to go up and to the left. And now I've got protactinium-231. And this has an alpha decay, 100% alpha decay, so I go down 2 and over 2, and I keep going, and I can just trace this out. Now I can look at the decay chart, or the decay chain, rather, of any isotope. We have a good understanding of that. We can look that up just by itself. But this resource from the IAEA is going to, once you type in the isotope that you're interested in, then it highlights all the important ones, either upstream of that as parents or generations in the past, or generations forward in terms of daughters and granddaughters, so to speak. And I can get the same thing from other resources. This chart of nucleides from Brookhaven National Lab. I can do the same thing here, and I can type in U235, and it zooms in here and it tells me, okay, I got 100% of an alpha decay. There's a very small percentage chance that I go through spontaneous fission, and since it's alpha, I can chart this out just like I was in the other one. I go down 2 and over 2, thorium-231. Well, that's a beta minus, and I go up here, and then I have alpha decay again, and so on and so forth. But each of these resources is going to be similar in any kind of data representation, just to show you here's the type of decay, and because you know what happens to the number of neutrons and protons in that type of decay, then you can trace out the process, trace out the decay chain. Okay, so let's calculate the Q values. Let's go back to our notes here and go through these 4. So let's talk first about a gamma decay, then alpha, and then our beta decays. So in a gamma decay, we've got this is the reaction here, and so if I'm doing a Q value type, of prediction here for the energy, then I've got the mass of that parent, rest mass of that, times the speed of light squared, plus I've got this extra energy because I am in an excited state, not in the ground state, and that's going to equal the mass of the product here, which also is the rest mass x times c squared. So you can see these, first of all, are just going to cancel out. And then I've got some kinetic energy of that daughter product, plus the energy due to the gamma radiation. So I have no change in mass, in the rest mass, so those two terms cancel out. And so my Q value here for gamma type radiation is going to be equal to whatever that extra energy was that took it from the ground state to an excited state for my nucleus. And so that's going to equal my kinetic energy of the daughter plus the kinetic energy of the gamma ray. And this energy of the daughter product, this is called the recoil energy. And you can think of it as I eject this gamma particle, then I'm going to recoil some with this bigger mass. But the recoil energy is usually pretty small. And so we oftentimes neglect that, so I get my Q for the gamma is just equal to the extra energy that I had there, which also equals the energy of the gamma ray. And so in this case, Q is always going to be greater than 0. None of these terms are ever going to be negative, and so if I have a nucleus in an excited state and I go through alpha decay or gamma decay, I'm never going to get a negative Q value. It's always going to be spontaneous. It always has the possibility to happen. In other words, that means without any energy input on my end. Okay, the second type is our alpha decay, and so I've got my parent here, and I lose a total of 4 nucleons, and so I've got the mass of the parent, and I have no no projectile, right? In any of these cases, this is all spontaneous decay. So I've got the mass of the daughter plus the kinetic energy of that daughter plus the kinetic energy of that alpha particle. This is my alpha, so the 4 helium, plus the mass of that helium, right? So the mass of H4 times c squared. And so I'm going to calculate my Q value due to alpha as c squared times the mass differences. So I've got my minus, or mx minus my minus the light particle, which in this case is alpha. And all of that's going to equal the kinetic energies. So the kinetic energy of the heavy and the kinetic energy of the light particle. So there's nothing here that we're doing, by the way, that is any different than any other Q value calculation that we've done. We're just looking at the mass deficit and equating that to the Q value and saying, well, we can also use the Q value to calculate kinetic energies. And so there's nothing here that's different, but we should note that Q is going to be greater than 0 when the mass of the parent is greater than the sum of the mass of the daughter plus the mass of that alpha particle. So if that's the case, then Q value would be positive. Then it is spontaneous. It doesn't need any kind of input from me. For a beta minus decay, what's happening in the beginning phases of this, if we look at this in stages, then that neutron changes to a proton, and that's what we're showing here. But I also have, initially, I have this +1 charge of the atom because I emitted that beta minus particle. And because I emitted that, then I've got a +1 charge of that atom, and this here is my beta minus particle. Again, we will call it. We'll use that nomenclature there, or beta minus. Those two are going to be equivalent. We will use a different label for the atomic electron in just a minute, but and then of course this one here is my antineutrino. And so what happens is that this is going to recombine with an atomic electron. And what that does is if I take this here, which is the daughter shown above, that is going to combine with an atomic electron, which we're going to use this label to denote that, rather than the label you see up above. And that is going to become now the neutrally charged daughter atom. And because I have that electron that is going to recombine in the nucleus, then I've got to emit some sort of gamma radiation, most likely an X-ray. And so this here is the atomic photon that is happening from that recombination process. And so what do I get? I take this now, and I have the following. I've got my beta minus particle. I've got my neutrino, my antineutrino. But then I also have this gamma sub x. And then the way that I'm going to account for that electron that I just mentioned from the atomic electron is just subtracted off this side. So that's my full reaction. In order to calculate the Q value, I've got to take the mass. There is the reactant side of the equation. That's going to equal the mass of my products. We'll do the kinetic energy of that daughter plus the mass of my beta minus particle plus the kinetic energy of that beta minus particle. And then I've got this neutrino, and as I was alluding to earlier, the mass of this neutrino is so small that we are going to neglect it. It's not going to make a difference in our overall Q value expression. So I'm going to neglect that, but I am going to account for the kinetic energy of that neutrino. And then finally I've got the kinetic energy of that gamma X, and then this electron that was from the recombination process that came from the atomic electron. So then I say minus, since that was a minus, the mass of that electron times c squared. And the beta minus particle here, this mass is the same as that mass. That is the mass of an electron. I've got plus, I got minus there. These two actually end up canceling out. And so what I have left for my Q value is going to be c squared times m capital X minus my. That's going to equal all these kinetic energies now. I've got the kinetic energy of the daughter. I've got the kinetic energy of the beta minus particle. I got the kinetic energy of the neutrino, and I've got the kinetic energy of that gamma. And these two here, again, the recoil energy, that's what that kinetic energy of the daughter is. That, along with this kinetic energy here, these are going to be much smaller than either the kinetic energy of my beta minus particle or the kinetic energy of that antineutrino. And so note here that my Q is going to be greater than 0 if this is true. And so my final expression here for that Q value is just going to be equal to c squared times mx minus my. And that's going to equal, neglecting these other two that are small, I've just got the beta minus kinetic energy and the antineutrino kinetic energy. So we'll say this is approximately equal to then. Try that a little clear. Okay, so that's my beta minus, the expression for Q value for beta minus. Go back up here to my expression for Q value for the alpha decay, and then this is my Q value for the gamma decay. So now let's go and do this for the beta plus decay. Again, I've got my parent, my daughter, and this is going to be, in this case I've got the minus 1, just like I had a plus 1 last time. I've got a minus 1 in this case. That's due from the beta plus particle getting emitted. This here is my beta plus particle. And this here is my neutrino. And so I've got this, it's not a recombination process, but I'm going to, what's going to happen is I'm going to emit an electron, an atomic electron. And so this here, that had a positive charge or a negative charge here is going to then be a neutrally charged daughter. plus that we just emitted the atomic electron there. So this is going to be an electron emission. And so just like before, we can replace this and look at the full expression. This is going to be my neutral daughter. And then I've got my beta plus particle, I've got my neutrino, and then I have this electron. So that's the full equation. That is my reaction. So let's look at the masses. The mass of X, that's going to be the mass of Y plus the kinetic energy of that daughter plus the mass of my beta plus particle plus the kinetic energy of that beta plus particle. And the neutrino, again, I'm neglecting the mass of that neutrino, so I'm just accounting for the kinetic energy of that neutrino. And then I've got the mass of that electron plus the kinetic energy of that electron. And these two here, my beta plus is the same mass as an electron. In the beta minus decay, those terms cancel each other out, but in this case we've got to add them together. They have the same rest mass, so we can add them together. And so my Q for the beta plus decay is just going to be equal to C squared times mx minus my. And then I have the other rest masses are the mass of the electron. So this will be minus 2 times the rest mass of an electron. That's going to be equal to all my kinetic energies that I still have at this point. Y plus the kinetic energy of that beta plus the kinetic energy of the neutrino plus the kinetic energy of that electron. And this term, and again the recoil energy, these are going to be small, just like they were before. Compared to the kinetic energy of that beta or the neutrino in this case. And so I'll neglect those, and eventually I'll have this new expression for beta, or for Q. Note that Q is going to be greater than 0 if mx minus my minus 2 me, or let's see, if the mass of X is greater than the daughter plus 2 electron rest masses. And so this ends up being just the kinetic energy of the beta plus and the kinetic energy of the neutrino. So this now is my Q value expression for beta plus decay. And then finally I have the electron capture, which is going to feel real similar to a beta plus decay, but what happens is I have since I'm capturing an electron, that's what initiates the proton conversion to a neutron. And so it leaves once I capture that neutron, then I have this excited state of the daughter. It's no longer at its ground state. So I see that captured electron is going to initiate proton converting to a neutron. Which would look something like this. A proton plus that atomic electron is then going to equal a neutron and a neutrino, just as the beta plus decay. And so what happens, since I'm in an excited state, then this is going to equal the same daughter in ground state plus I've got to give off some gamma radiation to go from that excited state down to the ground state, just like we showed above with our first type of radiation that we looked at. That was gamma radiation. And so this is going to feel real similar to that, or behave real similar to that. And what happens is I need to just, depending on which energy level I'm at, I might have one gamma ray be ejected or a series of gamma rays. And so in order to account for that, I just am going to sum these over J, depending on how many states of that excitation level I need to go through before I cascade finally down to the ground state. And so this then ends up being the daughter, as we expect, with a proton changing to a neutron, plus all these one or more, not all these, but one or more gamma rays going from an excited state back down to the ground state, plus that neutrino. And so what does the mass balance look like? Well, I've got mass of my parent, mass of the daughter, plus the kinetic energy of that daughter. Gamma, I have kinetic energy of all the gamma, but I don't have mass to those gamma rays. Do a sum there of the kinetic energy of the gamma rays. And then I've got the kinetic energy of the neutrino. And those gamma rays are generally small compared to the others. And so my Q value for electron capture is just going to be equal to c squared times mx minus my. Those are the only masses, the only rest masses I have there, and that will be approximately equal to the kinetic energy of the daughter and the kinetic energy of the neutrino. So we're going to go through a couple examples here, and we're going to bounce back and forth between doing this by hand, doing this with some piece of code, and then proving that the code is giving us reasonable results by looking at some of these online resources to verify that. So let's go to example number 1. In example 1, we've got alpha decay of U-238. We want to write an energy balance for the decay, and we want to determine the Q value. And so first let's write this energy balance, or we've got 238. Uranium has 92 protons. That's going to decay. It's an alpha decay, so I'm going to lose 2 protons, and I'm going to lose 4 total nucleons, and that becomes thorium. And then I've got my alpha particle, helium-4. And if I look at the mass balance, then I've got the mass of 238 is the mass of thorium-234 plus the kinetic energy of 234 plus the mass of helium-4 plus the kinetic energy of helium-4. And so this is the energy balance, the mass energy balance. And in order to calculate the Q value, I just take the difference in those masses. So the Q value is going to be c squared times the mass of 238 minus the mass of 234 minus the mass of that alpha particle. And I can go look up the masses either in a chart of nuclides, or I can use my own function that has the built-in data table that it's extracting information from, and I find out that this is 4.27 MeV. So if I go back to this nuclide chart from Brookhaven, then I can hover over this, and I can click on U-238, and I can see the energy levels, but this doesn't correspond to my Q values. I would need to dig a little bit for that, or I could use this same, instead of going to the chart of nuclides, I can just go to the Q value calculator and go to the decay. My parent here is U235, 238 in this problem. The decay mode is going to be alpha decay, and we look at the value over here and we get 4.27 MeV, so that's the same number that we got before. And I could look at different decay modes here, or I could look at a summary of this. I could type in 238, U238 here, and it will give me all sorts of information. I can look at the Q value for a beta minus. Now I know that I don't experience a beta minus. The fact that it's negative is evidence why that doesn't happen. Same thing with electron capture, same thing with beta plus. Now if I had a neutron, which we didn't talk about neutron or proton in terms of the Q value, but I mean it's just a balance of the masses just as before. A neutron or proton, where I can go down here to alpha, and that's what this value represents here. So notice that just because the Q value is larger for that doesn't mean that it's more likely to experience that type of decay. So we've only covered four or five technically different decay paths. There are plenty more than that, but it's not that I look at all this list and say, okay, those are negative, so it's not possible. It can't happen spontaneously unless I give some energy. What's the biggest one? Well, the biggest one must be the one that is the most likely, and that's simply not the case. It has a lot to do with so many other variables that are going to dictate what type of decay actually occurs. And so we know from the nuclide chart that we were just looking at that 100% of that is going to be alpha decay, and so this is my Q value for that decay. So every time one of those molecules, or any time one of those atoms of U238 goes through alpha decay, then it's going to release this amount of energy, 4.3 MeV. Or I could just look at, again, just at the decay process for alpha and see that it gives me the same number there. So I could also go to this resource from the IAEA, and I could look at 238 here. Click on that one, and I can look at this. This here gives me the list of those same Q values. You can see I see that alpha is 100% of the decay mode, and so I go to Q alpha for 4.27 MeV. I could also look at the decay radiation down here. And this, we'll get back into this towards the end of this lecture today, but it's gonna show you this energy level diagram that tells you more of the sub processes that occur along the way and how likely each of those are, and so on and so forth. But I have all these values for Q, and it really boils down to this column here that tells me the likelihood of different paths. And so there's only two paths listed here. Alpha is 100%, rounded off to 100%. In reality, there's a really, really small fraction of a percentage that I could go under spontaneous fission for this. And then similarly, I have different decay modes for uranium-238 if it were in its first excited state, first nuclear excited state, so from the ground state. And that would be an energy level of 2.5 or 2.6 MeV. And so I'm going to, when I go from that excited level down to the ground level, that'll be 2.6 MeV. And then when I go through an alpha decay, whenever that happens, then I'll get this another 4.3 or 4.27 MeV there. So let's look at, let's build ourselves some calculators here. And I'll step you through what I've done here. This Q value function is just one line long, right? All it did, and this was something that we created early on in another lecture. But what this does is just take the mass of its two reactants and two products, and I just take the reactants masses and subtract the product masses from that, and this 931.5 is what's going to give me this value in units of MeV. Now I have another function, this AMU lookup function, that I can express each of these inputs in terms of their number of neutrons and number of nucleons, the Z and the A, and that's typically how you would extract information from a chart of nuclides anyway. And so what I've done here is create myself a function where I can do just that. I can say, just tell me what the Q value is, and I'm going to call this function decay Q, and I want the inputs to this to be the number of protons in the parent and the number of nucleons in the parent. And the other input to this is this type, which I'm going to specify as either A for alpha, BM for beta minus, BP for beta positive, or EC for electron capture. And so my outputs to this function are going to be the number of protons in the daughter and the number of nucleons for the daughter, and then of course the Q value. And so if I have type A, if it is a alpha type decay, then I know that my protons is going to be 2 less than it was in the parent, so my daughter protons is just 2 minus whatever it was for the parent, and then my total number of nucleons decreases by 4, and so I can just use that function, this Q value function that I already created, and in the first input I will use my AMU function to get the mass, because the inputs to this need to be units of mass, not number of nucleons or protons. But with the number of protons and nucleons in the parent, I can look up the AMU value. That is the heavy reactant on the reactant side of the equation. And then my target, so that was my target. My projectile is 0. I don't have any mass there at all. I don't have a projectile. And so I just type 0 in for that input in my Q value calculator. And then I will, for the product side, the light product is going to be the alpha particle. And so that has a number of protons is 2, number of nucleons is 4. And then I need to look up what I calculated as my updated numbers for my daughter and get the mass of that one. And then my Q value is just whatever it ends up being for those masses. And I do something similar for my beta minus. I know that my number of protons is going to be whatever it was for the parent plus 1 because I had a neutron changed to a proton, but my number of nucleons stays the same. And just like I did before, this Q is going to be calculated based on that simple Q value expression where I look up the mass of the target, which is the parent, and I have no projectile, and in this case I have no light particle. The mass of the light particle is 0, so the mass of that neutrino is negligible. So going back to our expression for the Q values, let's look here at the beta minus. So this here is the expression that I am wanting to calculate a Q value for. And so I don't have another mass. I just have the heavy particle on the reactant side and the heavy particle on the product side. And so coming back here to my function, I can put 0 in for that light particle and then just look up the mass for the daughter. Same thing for the beta plus, only instead of a proton increasing by 1, the proton count decreases by 1. The number of nucleons stays the same again, and this function looks awful similar to that. But if we go back to the expression for my beta plus decay, notice I have these extra 2 here. I've got my extra 2 electrons. That's the difference between the Q value expression between beta plus and beta minus. And so what this is here, I have 2 times, this is the MeV. So if I take the rest mass of the electron, and if I multiply that by 931.5, then I get 0.511 MeV. And I've got 2 electrons, and so that's 2 times 0.511. And we're gonna see this later on as well. If you have an electron and a positron, when they come in proximity, they annihilate each other, and the energy that is released during that annihilation process is the rest mass of those 2 particles, both having a rest mass of the mass of the electron. And so you'll get 2 gamma rays, each of 0.511 MeV in that scenario. But this much here in the expression is going to give me the Q value that without accounting for those electrons, and then I just and this will be an MeV, and then I just subtract the MeV of those 2 electrons from that expression. And then finally, electron capture does the same as beta plus. I lose a proton to a neutron, my number of nucleons stays the same, and I don't have to worry about these extra 2 electron masses here. And so I get my Q value there. And so literally all I have to do is say, because I don't need to tell the function what the daughter is, I just need to tell the function what the parent is and what type of decay it goes through. And because I know the type of decay, now I know what the daughter would be. And so I can use this function here. Let's do U238 again. So 92 and 238. And the type is going to be alpha. Forgot to type decay Q is the name of the function. And I need to give it more outputs. So that's going to be Z, Y, and Q. So the daughter product is going to have protons of 90, it's going to have a number of nucleons of 230, and the Q value is exactly what we calculated by hand and saw from those online resources. But I could also just assume that I have a beta minus, and that's negative 0.1474. If we go back to here, we find that the beta minus Q value is negative 0.147 MeV. And so the calculator seems to be giving me numbers that are correct. Let's go look at beta plus, negative 4.6 MeV. It's not listed because you see that you see here in the list of decay modes, it's listing these 2 together, beta plus and electron capture. But I can certainly do the electron capture. And I get negative 3.58. And I compare that to this, my electron capture negative 3.586 MeV. So this calculator is convenient. We'll use this in the second example. You're encouraged to create such a calculator. If you know what type of decay occurs, then you can simply just type in the number of nucleons and number of protons and then let the calculator do the rest for you. But there's nothing preventing you from just doing this on any of these online resources as well. It's going to give you the same numbers. It's just a matter of later on, if you need to do homework assignments that you need to cycle through these again and again and again, then it's nice to have a function like this that evaluates all that for you. So let's go to example 2. So here in example 2, we want to calculate the Q value for each of the 4 decay processes. So we've got bismuth 211 here, and this is organized according to what you would see direction-wise in a chart, in a nuclide chart, meaning beta minus is going to go up and to the left, alpha is going to go down and to the left, those are the only 2 that we have there. So if we look at isotope at A, then this is going to have two, or it's a beta minus, so it's going to have one more proton. So Z is going to be 84, and my number of nucleons does not change. Isotope B is going to be an alpha decay from that isotope A. So my number of my number of protons is going to go down by 2, and my number of nucleons is going to go down by 4 from that 207. And let's look at isotope C. Isotope C, if I go from bismuth down, an alpha decay, so my Z is going to decrease by 2, going from 83 to 81. And my number of nucleons decreases by 4 from 211, so that goes to 207. And then finally isotope B, which I could arrive at that from C, or I could arrive at that from A, and I should get the same thing. So here we found out that isotope B had 82 protons and 207 nucleons. And if I look at now the beta minus decay from C going to B, then that's exactly what I find. I get one more proton, and my number of nucleons does not change from what it was in isotope C. So let's go and calculate our Q values. Let's use this calculator here. And so my initial bismuth 211, I'm going to have 83 protons, I'm going to have 211 nucleons, and so I can just call that function that I just stepped you through, that decay Q, and I can start with that Z naught and A naught. And if I go to from point 0, which is bismuth 211, to isotope A, go through that, that's a beta minus, so that will give me the ZA and the AA, Z and A at that location A, and also the Q from 0 to A. And then I'll do this again for point B and point C, and then I'm going to do it twice for point B, approaching it just like I did a minute ago from point C rather than point A. So I go from A to B, and then I go from C to B. But I just need to make sure that I'm using the inputs, which for each process I have a different parent, and so make sure I have those in properly, and then make sure I'm labeling this third input with the type of decay that is illustrated in the figure. And so now I can just run this, and if I look at Q here is going to be Q from 0 to A is going to be 0.573. From 0 to C, that's going an alpha decay down, that's going to be 6.75, and then A to B is 7.59, and finally C to B is going to be a Q value of 1.41 MeV. And if I look at the number of, let's take the number of protons. Started with 83 at the top corner there with bismuth 211. If I go to point A, I increase that because I had a beta minus decay. If I go from A to B, I've got an alpha decay, so that's going to decrease by 2. And then I look at C, going from bismuth, which had 83, it's an alpha decay, I lose 2 down to 81. And then I go from point C back to point B, that's what I'm calling ZB2. I increase my count by 1 again, and so the fact that ZB and ZB2 are identical is good news, meaning that this is a loop, so to speak. And the same thing with the total number of nucleons. I should get the same for AB and AB2. So I've got all those Q values now. I can write those down. So Q value here from 0 to A is going to be equal to 0.574 MeV. The Q value from A to B was 7.595 MeV. Q value from let's see, this would be from A to A, or from B to, no, from state 0 to C. And then finally I've got Q value from C to B. And those are going to be equal to 6.750 MeV, and from C to B was 1.418 MeV. And we could have approached this a different way. We could have looked, since this is a loop, so to speak, we could have said that Q from 0 to A plus the Q value from A to B has to equal the Q value from 0 to C, coming down here, that alpha decay, plus the Q value from C to B. So we could have operated this just by calculating these three and then not knowing that one, and we will find out that we get the exact same answer in both cases. All right, so for our final example, example 3, we want to look at this decay chain. And so we have uranium-235, and we're going to decay, it's going to be an alpha decay down to thorium-90, and that's going to then have a beta minus decay up to protactinium-231, and that's going to go down to actinium-227, then up to thorium-227, or down to an alpha decay down to francium. So the question is, what do we do here? And this is the statement that for this problem, if there's multiple decay paths open, because sometimes you'll find that there is a 90% chance of this one, a 10% chance of that one. Sometimes it is very clear because it's 100 or very close to 100% down that ratio, in that branch. But so for this, we want to consult the chart of nuclides and see what's the most likely path, and then follow through from there. So we know that we're going to start with U-235, and that's going to go through an alpha decay to thorium up to protactinium, and then we're going to arrive here. So let's now go to actinium-227. Go to actinium-227. That's here. And so as I hover over this, we see that there's a beta minus and an alpha, just as it was shown in the decay chain diagram of this problem. But obviously the most dominant mode is my beta minus decay. And so I come back here, and I'm going to highlight this. I'm going to go to the thorium-227. And then that's going to alpha decay to radium-223, which is also going to alpha decay down to radon-219, which also alpha decays down to polonium-215. And then I've got an alpha decay down to lead-211, and then a beta minus decay. So let's go to polonium-215. This is essentially saying alpha is 100%. And in a decay chain diagram like there is on this problem, you can see that this line here is a dashed line, which means that this is not likely at all, but it's not zero. It's very close to zero, but not zero. But at any rate, since this problem we're just looking at the dominant modes, we'll go through another alpha decay down here, which then we have a beta decay. And we can see a dashed line going up to polonium-211. So we can go prove to ourselves in the chart of nuclides that that's the case. But eventually, we're going to go through another alpha decay down to thallium-207, which then beta minus is decay up to lead-207, and that is the stable isotope. That's what it's eventually going to become. Now you see in each of these circles there's also a time frame listed. That is the half-life, which we'll cover next lecture. But a long half-life means it takes a long time for that decay to occur in a given sample. And so, we're going to calculate the Q values for each and every one of these, and then the total Q value, we're going to get some number, and that's going to represent the total Q value that would be the energy that would be released going from uranium-235 all the way to lead-207. But that's going to be done in pieces, and it's going to be done sometimes very long time frames. So you can see radon, for example, has a half-life in seconds, so 3 and some change seconds, 3.96 seconds. So that's going to be awfully quick, but then you've got these other ones that are, 3e to the 4 years, and we got days, and then 7e to the 8th, finally, for U-235. So let's go to we'll make use of this calculator again. And for this one, all we need to do is start with U-235. And we'll let the calculator tell us what the new daughter is every time. All we need to do is tell it what kind of decays we experience each time. And so for the paths that I just highlighted on this example, we just step through those alpha, beta minus, alpha, beta minus, alpha, 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 beta minus, alpha, beta minus. And so that's all the information we need. And I'm just going to say the Q, my first element in that Q is going to be 0, meaning that I'm not in an excited state, I'm just at the ground state. So as we step through this, then all I need to do is cycle through. And in this case, I'm going to start with index number 2, and I'm going to go however long this vector is. This is a vector of string variables, basically. How many ever elements that is, that's how many decay processes I have. But because I'm starting at 2, I need to increase this by 1 as well to get to the final result. And then all I do is just calculate a new Z value, a new number of protons. I calculate the new number of nucleons. I calculate a Q value for each one of those processes. And the decay function is just going to call the number of protons I had in the last loop, so the last parent. And this now is the new daughter. And so it's just going to cycle through that again and again and again, using a different decay path each time according to this third input into that function, which is my decay type. So with that function built, this is really a short problem. It's I've got my Q value here. I can look at this. So this is for my first decay process, going from uranium down to thorium, and so on and so forth. These are the actual Q values. You notice that none of them are negative, which we wouldn't expect them to be negative. We expect them all to be positive. We're saying this is a spontaneous decay process. But I could take the sum of that whole vector and find out my total Q value there is 46.398. And again, that's going to happen over many years, but that's that one molecule or one atom of uranium-235 as it goes through all these decay processes and becomes finally a molecule or an atom of lead-207, then I have released this much energy, 46 and some change MeV. Okay, so that's the third problem. Let's just spend a little time now talking about energy diagrams. And so going back to this one from IAEA, as I looked at the, I'm at U-238, let's take a look at, let's see if a good example might be cobalt. In the textbook, it's going to show you cobalt-60 as an example for these energy diagrams. And if I go to here to decay radiation, so this particular radioisotope is going to go through a beta minus decay. It's going to have a half-life of 1925 days. It ends up being a little over 5 years, I think. But if I scroll down a little bit, I see these other plots. Let's just talk about those for a minute. So we mentioned before about this is a beta minus decay, and so we're expecting a beta particle and then an antineutrino. And the kinetic energy that is released, remember I don't have much of kinetic energy recoil in the daughter product. It's mainly going to be deposited in that beta particle and the antineutrino particle. And so because it's something like this, if we experimentally measure this again and again and again, and we realize there's some distribution to this, then the only logical explanation for that is that there must be some other particle, must be a really small mass because it's hard to measure, but there must be some other particle there that's accounting for other bits and pieces of that kinetic energy. So in order to maintain that momentum balance, I have to have something there. In this case, it's an antineutrino. So if I scroll down a little bit, then I'll see this energy level diagram. And we expect this to go to the ground state, eventually cobalt 60. If it goes through a beta decay, is going to be nickel 60. Notice my proton count changes by 1, my neutron count changes by 1, but my total number of nucleons doesn't change. That's what we expect for a beta decay. I could prove that this is the case with my calculator, that I have 2.82 MeV that is released as part of that beta minus decay. But what we see from this energy level diagram here is that eventually, yes, I do get to that ground state of nickel 60. But what you're seeing here is different energy levels of that nickel 60 nucleus. And so what we find is that 99.88% of the time, it actually is not going straight to the ground state. It's going up 1, 2, 3 energy levels for this nickel 60. And so it's going from cobalt 60 at ground state to an excited state on the third excited state of that third level of that nickel 60. That's where almost all of it's going. 0.12% is going to go down to the first energy level, and so we see going to the first energy level. Then I release some amount of that 2.82 MeV. And then when I go from that first energy level down to the ground state, I release the rest of it. And likewise, when I go to that fourth energy level, there's an opportunity for me to go straight down from the fourth all the way down to the ground state. I could go from the fourth down to the first ground state, or I could go from the fourth down to the, or not the fourth, I meant to say third in all that case. Third down to the ground state, third down to the first, or third down to the second. And that's how much energy is released in each one of those transitions. And so this is useful to understand the sub-processes that we don't oftentimes write down on paper, but is part of the overall decay process that happens going from one radioisotope to another. So you can look this up for other isotopes. We'll do maybe one more. Let's do an alpha. Let's go back to U-235. And the decay radiation tab here is showing us that there are a lot of levels here. And so what looked fairly simple and straightforward for cobalt 60 is a sweet mess, not a sweet mess, but is much more complicated for uranium 230, what am I at, 230, can't remember what I did, 235, yeah. So for uranium 235, 100% of the time I'm going to have an alpha decay, and it's going to go to thorium 231. But I've got many, many energy levels for that thorium 231. And we can see that most of the time I'm going to, right here, so a little over half of the time, I'm going to go to the fifth energy level of that thorium 231 nucleus. And the second most common is going to be up here at the seventh energy level. And then I've got some that are similar to each other. Got one that's 6%, and anyway, you add all these up and you get 100%, obviously. But yes, it's an alpha decay, and yes, it's always going to be thorium 231 in the ground state, and that 4.68 MeV represents the full transition from a ground state U-235 to a ground state thorium-231. But we can see that the energy levels in many cases are going to be done in steps. So eventually, yes, we're going to get to that 4.7 MeV, but it's going to be in steps along the way. So other resources, other charts and other online resources have this information. I find it most clean when looking at the one from the IAEA, and so that's why I chose to use this one. But you can get these in the Brookhaven lab. You can get them from the Korean. Actually, I don't know if the Korean one has it or not. I'll have to look and answer that later. But most of these, if not all of them, are going to have these energy level diagrams. And for the intents and purposes of the example problems that we just did, I mean, this stuff doesn't matter really. As long as we know that it goes down to the ground state of that thorium-231, then the Q value of 4.68 MeV, that's all that we really need to know. But it's more comprehensive and useful to understand all the sub-processes along the way. So that concludes this lecture. We will see you again for lecture 11.